Wow.
No, we talked.
Jeez. Wow.
That's not even the worst story about that.
Not that one. The other one. No.
I love this response. That's not even the worst part of it. I don't know what you're talking about.
Not the one, remember he said he wasn't ready and they took it anyway?
I don't know what you're talking about.
Now I just sound so mean.
All right. So here's the key for the homework. Go ahead and check your answers, folks.
People want to get home like I'm tired.
So remember, we're working with E, the natural base, mostly with half-life in this homework. Okay. You know, I might do 17 or 18. Some of the ones down below, 17, 18, 19, or 20, a little bit different. That's okay. I'll show them a little bit different than the key. But 12 was odd because you had to find the K value, and then not just find the K value and find, you know, in the notes we found the K value, and then we found, you know, how long it would take to get to a certain amount. This one, it was find the K value and then say, okay, after this long, what's left over? So you didn't really have to solve for anything. You just had to plug in 24 in this case. But you did have to solve for the K value first, given the half-life. Here's 15 as well. And again, I do want to talk through 17, 18, 19, 20. I would write them just a little bit different. You know, I guess 17 is fine. You'd say e to the what power is 0 or e to the 0, which is just 1. I would say here, you know, this would be turned into log base e of e to the 2a, which means that would cancel, leaving just a 2a. That's the way I would write it. Okay. Same thing here. E to the ln of c plus 2 is really like saying e to the log base e of c plus 2, which means that will cancel, leaving just the c plus 2. For number 40, I would want to take this 4 and put it up on top, and that would turn it into e to the log base e of x to the 4th, and that would cancel, leaving just the x to the 4th. Again, that's not wrong the way that the work is shown up there. I would just do it a little different. Number 21, you got to use the PERT formula. Remember, PERT formula is when I'm saying something is continuously compounded. That's the key piece of information that you need to know. When I say, because on the test on Thursday and Friday, I'm going to be asking you, you know, not only questions about continuously compounded, but also just regular exponential growth and decay. So you don't want to mistake something for exponential growth and continuously compound. Okay? How do you know the difference between the two? Well, I have to explicitly say the phrase, and the account is continuously compounded. You know, I have to use those two words, continuously compounded, for you to be able to use the PERT formula. It happens every year. A lot of people try to use the exponential growth formula, that a times 1 plus or minus r to the t power. They try to use that on the continuously compound, or you try to work it backward. You try to use, even though it doesn't say continuously compound, you try to use the PERT formula. Well, that's not necessarily true for all exponential growth. Okay, so you need to know the difference between the two problems. I have to use the phrase continuously compound for you to use the PERT formula. Okay, here's 22. Let me scroll down here. There we go. 22, 30, 32, 34, 36. Number 22 is a lot more like the ones that we had done in class. We had to, it's that same half-life, that 24,110. But you get the same K value there, that 0.00002875. You use that to find how much is going to be left over after 5,000 years. And then say, okay, if that's left over after 5,000 years, this is how much it's going to be, how much it's going to take to get from 20 grams down to 1 gram. I'm just showing here, if you did not just use that rounded answer, that's what you would get for the years. Okay, if you had kept it in your calculator, if you kept it stored in your calculator and used that K value within your calculator, that's the unrounded piece there, 104, 201.69 years, 104,000 years. Crazy, right? And then there's 32, 34, 36. Remember, the rules for ln are exactly the same as the rules for logarithms when you are going to solve for them. So subtraction means division, addition means multiplication, bringing a power means that you can bring it out front and multiply. Okay. Any questions through 36 so far? Yes. Yeah, so remember that just because it's got an ln, it doesn't, you can solve it the exact same way as if you had said, if I had given you this, log base 3 of 5 minus log base 3 of x is equal to 3, you would probably figure out how to do this. 5 divided by x is equal to 3, and then change it from logarithmic form into exponential form. 3 to the third is equal to 5 over x, and then you just solve that equation, right? So the only thing I'm changing here is now I'm saying that this is log base e. And it works the exact same way. And now instead of 3 to the third, it's just e to the third is equal to 5 over x. Okay? That's the only difference there. And now we just solve this equation, because e to the third is just a number anyway. So I multiply the x over to the other side, x times e to the third times is equal to 5, so x is equal to 5 divided by e to the third. Looks like it's 0.25. Okay. So remember that ln is just log base e. You can work with it the exact same way we had worked with everything else back in section 7.5. Same thing here with 34. If I've got 2 ln of x minus 2, 2 ln of x minus 2 is equal to 0. Well, I've just got to solve for x. So let's get the 2 over to the other side first. 2 ln of x is equal to 2. I can just divide by 2 to get ln of x is equal to 1. I don't need to make that a squared. I don't know why we did that there. I forgot my x. ln of x is equal to 1. So I can say e to the first power is equal to x. Okay. Let's change it from logarithmic into exponential. And then the same thing is there true for 36 there. You could say e to the log base e of x to the third is and then that will cancel, leaving just x to the third is a cube root of 8 is 2. So you're just kind of bringing back everything that we learned back in section 7.5 and just applying it to now log base e as well. And then here is 25. This is that cool one where the temperature, the surrounding temperature, is acting on the hot liquid. Okay, it's cooling the hot liquid at a certain rate. So its total temperature is equal to surrounding temperature plus the difference in temperature times e to the negative kt, where k is the cooling constant based on the liquid. Okay, based on the composition of the liquid. So we're told that k value is negative 0.28, or just 0.283, so it's negative up in that exponent. And then it says, okay, well, what if the, what if I want the final temperature to get down to 140 degrees? The surrounding temperature sitting in a room is 70 degrees, so that's why T sub S is 70. And then we say, okay, well, I sat it on the table and it was 206 degrees. So I subtract the difference between the original temperature and the surrounding temperature, which would be 136 times e to the negative kt. And then so I just solve that. Subtract the 70, divide by 136 to get this equation here. You don't need to actually divide out the 70 divided by 136. And I think get that as a simplified fraction because it works the same way. But you would say log base e of this is equal to the exponent. So you'd say log base e of 70 over 136 is equal to negative kt. Divide by negative k, and you should get your minutes. 2.3 minutes or 2 minutes, 18 seconds. I just think that's an interesting problem in that, it's that idea of the surrounding temperature is constantly acting on the hot liquid, constantly cooling the hot liquid. So there's got to be some sort of E factor involved. There's got to be some sort of constant involved. All right. We hit out the guided notes for today. You guys will find, well, I guess I hope you'll find, in my opinion, section 7.7 and 7.8 are rather easier sections, just because we've learned everything within these sections so far. Okay? Section 7.7 is transformation. Now, we may need to brush up our memories on transformations. We may need to kind of dust off the cobwebs a little bit. But honestly, we've been there. We've done this. You know, we've been doing this with every single type of new function that we've had this entire year. And then section 7.8 is just running regressions with these things, which again, we've been doing the entire year. We've been doing this the entire year. So all we're doing now is applying what we know from earlier to what we've learned this chapter. All right. We can perform the same transformations on exponential functions that we performed on polynomials, quadratics, and linears. And in my opinion, these transformations are way easier than working with polynomials. I mean, the last new function that we learned was polynomials. Okay, that was the last new function that we learned, was polynomials. So now, you know, thinking into exponentials, there's not much simplification that we can do, because we can't really operate with things in the exponent with things outside of the exponent. So we can't, there's not really simplification that we can do, which, to be honest, there was a ton of simplification that we had to do with our polynomial functions. All right, so let's take a look. Now, you'll notice here that the inside column there, that f of x notation column, is not new. All of the middle column is all the same notation. Vertical translation, f of x plus k. Horizontal translation, f of x minus h in parentheses. Vertical stretch compression, a times f of x. Horizontal stretch compression, 1 over b, x, inside the parentheses. Reflections, got the negatives going on. One's inside, one's outside. Reflection across the x-axis, negative on the outside. Reflection across the y-axis, negative on the inside. None of that is new. What's new is how we apply it to the exponential. So let's take a look. If you've got anything vertical, see, take a look at these pieces in here. If you've got anything vertical, and the vertical is the reflection across the x-axis. If you've got anything vertical, take a look at these pieces. What do you notice about all those pieces? All of those things are happening down below. They're not happening up in the exponent. All of those things are happening to the base. Okay? All of those things are happening to the base. Take a look at everything horizontal. The horizontal translations, and then the horizontal reflection. Where is all of that stuff happening? In the exponent. Okay? The unique thing here is everything horizontal is contained up in the exponent. Anything vertical is happening down below. Okay? Addition and subtraction means the translations. Multiplication means the horizontal stretches, the stretches and compressions. And then obviously negatives would denote a reflection. Okay? Now, here's one thing that I wanted to point out. This is all assuming, within this table, this is all assuming that we got our parent function, y is equal to 2 to the x. Let me ask you this question. I want you to think about it. Should anything ever change the base? Or what would the transformations be that would change the base? Is there anything that would change the base? The answer to that question is no. Nothing should ever change the base. You may be thinking to yourself, whoa, what about this guy right there? Wouldn't that make that a 12 to the x? No, because the exponent is acting before the multiplication. Please excuse my dear ancestor, right? The e becomes before the m. So the exponent is acting on that 2, so I cannot multiply with it. Same thing here. You cannot multiply the 1/2 and 2 together right there. Now you got to be careful about that. A lot of people are going to try to change the base. You should never change the base of anything that I give you. Okay, when I'm telling you how to do a transformation. Like for example here, make a table of values graph g of x is equal to 2 to the negative x plus 1, and let's describe the asymptote, tell them how the graph is transformed from the parent. See, the parent is 2 to the x. You see the base on our new? It's a 2, right? The base does not change. No transformation will ever change the base. What's happening around it, that's the transformation. All right, so it asks us to make a table of values, so let's go for it. Let's make a quick table. Let's plug in some numbers. I've got 2 to the negative x plus 1. All right, 2 to the negative 2 plus 1. I've got 5. And then we'll do the same thing. 2 to the negative, entry. 2 to the negative 1 plus 1 is 3. 2 to the negative 0. Well, 2 to the 0 would be 1 plus 1 is 2. 2 to the negative 1, which is 1/2 plus 1 is 1/2. 2 to the negative 2, which would be 1/4. Plus 1 would be 1.25. All right, so we have negative 2, comma, positive 5. We have negative 1, comma, 3. We have 0, comma, 2, 1, comma, 1.5, and 2, comma, 1.25. Now, do we see the exponential? Looks like it's a decay on this one, doesn't it? Or is it going downward? The reason it looks like it's an exponential decay is because there's a reflection happening. What's the reflection? Reflection across the what? Reflection across the y-axis. So we're describing the transformations now. Reflection over the y-axis. And then what other transformation do we see? What's a plus 1 sitting down out of the exponent? It's an up 1. It's an up 1. Now, the last question says, well, I guess it wasn't the last one. I kind of skipped by it. It says, describe the asymptote. Describe the asymptote. That's going to be extremely important. Describe the asymptote. Let me ask you this. Where was the asymptote of 2 to the x? The untransformed 2 to the x. Where was the asymptote? Where? At 0. At y equals 0, correct? And it's important that we say at y equals 0. We can't just say 0 at y equals 0 because it's a horizontal line. All right, so if I shift that up 1, even the asymptote gets shifted up 1 as well. If I shift the entire graph up 1, the asymptote gets shifted up 1 as well. So I can say that the asymptote is y equals 1. When I say describe the asymptote, I'm asking you to either tell me what happened with the asymptote, or more likely give me the equation of the asymptote. Okay, well then let me ask you this then. Let me ask you this. So we see that the asymptote was a y equals 0 and it shifted up 1. That changed the asymptote. Okay, let me ask you this then. Will a shift left or right change the asymptote on an exponential? No. Because moving a horizontal line left or right doesn't really do anything. Okay, would stretching or compressing it change the asymptote? I don't know. Let's check. Let's see. Let's take a look. Graph the function, find the y-intercept in the asymptote, and describe the graph, how the graph is transformed from the graph of the parent. Let me ask you this first off. What is the parent function? What was the parent of this one? What was the original of this one? 1.5 to the x. How do I know that? Because nothing would have ever changed that. F of x would have been 1.5 to the x. You may be thinking to yourself, well, how did I go from 2 to 1. No. We don't always start from 2 to the x. Right? That's just one of the most basic ones that we can have. So we got 1.5 to the x. So what's the only thing that I'm doing? What's the only thing that I'm doing? Before I even graph, what's happening to 1.5 to the x? Being multiplied by what? 2/3. Where? Down below or up in the exponent? Down below. If it's down below, it's got to be something vertical. So we can say that this is a vertical. Now, since I'm multiplying by 2/3, compression by 2/3. Okay. Well, let's take a look here. I don't have my an actual graph on here because I wanted to show you that you can use your graphing calculator. So you can just sketch this onto your graph. But I've got here 2/3 times 1.5 to the x. Zoom 6. Okay, so here's my graph. And you can just transfer it onto your paper there. Let me go back. Let me scroll back up so we can identify all of the information. Graph the function, check. Find the y-intercept. How do I find the y-intercept? What would I do to a function to find the y-intercept? Plug in x equals what? Plug in x equals 0. Okay, if I plug in x equals 0, what do I get? 0 comma what? 2/3. Yeah. So the y-intercept is 0 comma 2/3. And the asymptote is, well, did I change the asymptote? It was at y equals 0. Did this vertical compression, which is pushing things down toward the x-axis, or the x-axis, did that change it at all? No. It's still at y equals 0. And again, when I ask you to give me the equation of the asymptote, I want an x equals or y equals. Don't just give me a number. And you'll see why here in a second. Describe how the graph is transformed. We did that. That's the vertical compression by 2/3. And there it is. We've done everything, I guess. There we go. Questions about that? Let's do that again. Oh, still that way. Does it change anything now that I've got my e to the negative x plus, and that I have an e for the base? No, the only thing that is different is now what is the parent? What's the parent now? E to the x, right? I know my original function was e to the x. I don't really necessarily need to know that to describe what's happening. Let's describe the transformations. I see a negative x and then a plus 1. Negative x and then a plus 1. Now, this one is kind of unique. Because I could think of this in two different ways. What's the negative telling me to do? Up in the exponent, what's the negative telling me to do? Reflect which way? Across the x-axis or y-axis? The y-axis. Reflect across the y-axis. Doesn't changing the x value. Reflect over the y-axis. And then, what's this? Left 1. Let me go into my calculator and graph this. I've got e to the negative x plus 1. See, it's interesting here. where is the y-intercept? Well, let's plug in 0, comma, this would be e to the negative 0 plus 1, which would be e to the first power. So 0, comma, e is my y-intercept. You could say 0, comma, 2.718, but I'd rather just write e. And then where is the asymptote? Y equals what? Did it change at all? And let me just do that. Let me throw this guy out of the way. And bring this guy over here. Did my asymptote change at all? No, because I didn't do anything really vertical with this thing, shifting up or down. Now, what's unique about this one is that I actually should have said, if I can move this, yeah. I actually should have said left one, then reflect. I actually should have said left one, then reflect. Because you know what else I could have said? I could have said reflect then right one. And here's why. I could have rewritten this. I could have said e to the negative x minus 1. Doesn't that mathematically come out to be the same thing? Negative x plus 1. Okay, depending on the order at which you take these things, it's acceptable to write both of them, actually. Okay. All right. Let's flip it over onto the back. Let's talk about the logarithms now. Because a log is an exponent, transformations of a logarithm functions are very similar to transformations of exponentials. You can stretch, reflect everything just like we had on our exponentials. So again, look at the middle column. The exact same thing, even that you had on the front side of this. Okay? It's the exact same thing. Now, here's the difference. Here's the difference. Okay? We said that anything vertical was happening down below to the base, right? So what I'm saying now is anything vertical is going to be happening to the logarithm, because the logarithm really is like kind of the operation, right? So the anything happening vertical is happening to the logarithm. Anything happening horizontal is happening within the logarithm, because it's anything horizontal is happening within an exponent. So it's happening within the logarithm, because what's inside of the logarithm is technically up in the exponent. So anything horizontal is happening inside the logarithm. Anything vertical is happening outside the logarithm. Okay? Now here, please be very particular about how you use parentheses. Because I would have people try to tell me that this is a left 3. Because they see, oh, it's log of x plus 3. Be careful. If this was truly a left 3, this would be a log parentheses x plus 3 end parentheses. Okay? Be careful with that. Make sure that you know that if there's no parentheses, then the only thing that log is acting on is the thing directly to the right of the log. So this is log of x plus 3. Okay? Dramatic pause. All right, let's take a look here. Graph each logarithm, find the asymptote, describe how the graph is transformed from the graph of its parent. All right, I've got 5 times the log of x minus 2. Go ahead and guess what you think is going to happen. I want you to write down the transformations that you think is going to happen. What's happening here? What do you think the 5 is doing? What do you think the 5 is doing, sitting on the outside? Vertical stretch by 5. What do you think this minus 2 is doing? Down 2. Again, I'm going to graph it on my calculator here. 5 common log x. And my parenthesis, be very careful about that, minus 2. Okay, now let me ask you this. Think about where the asymptote was. Think about where the asymptote was for a logarithm. You know, the asymptote for an exponential was at the y equals 0. The asymptote for a logarithm was at the x equals 0. Does it transform away from the axis? In this case, does it transform away from the axis for this particular one? No. It didn't. Look, the asymptote is still there. I didn't move it at all. Okay? So when it says to describe the asymptote, find the asymptote, you would say the asymptote is at x equals 0. And again, it's very important that you write x equals, because the exponential asymptote is going to be a y equals, always. So therefore, the logarithmic asymptote is always going to be an x equals. So it's going to be a vertical line. Now, so if those two transformations didn't change the asymptote, can somebody tell me what type of transformation would change a logarithmic asymptote? What type of transformation would change the asymptote from x equals 0 to something different? A left or right shift. Anything that's going to move it left or right. Now, let me ask you this. Is this going to move it left or right? So should I see a change in asymptote here? I should. Now, it's got this funky thing with a negative on the inside. So I see two things. I see a reflection over the y-axis, and I see a left 2. And I'm actually going to write it in that order. Okay, let's take a look. I'm going to plug it in. I've got ln of negative x plus 2. Now, we know better than this graph, don't we? Does it actually stop? No. See, when you graph it, see, this is the case where, like, when I ask you to graph these things on your actual test, if you stop, I would take points off. If you make it look like your calculator, I would definitely take points off, because that shows me that you're trusting your calculator too much and you don't really understand what's happening with the logarithm. And again, don't forget, what's happening here with your calculator is it's running numbers and it's getting so close to 0, it thinks it stops. But it does not stop. It will continue forever here. All right, so now, did my asymptote change? Yeah, my asymptote changed. Now, it looks to be right here. Where is that? Where is my asymptote now? At x equals 2. Good. The asymptote is at x equals 2. Well, wait a sec. I said left 2. Shouldn't it be at negative 2? Well, I shifted left, then reflected it over the axis. So even though I shifted it left, it then reflected over back to the right. See, the other option I could have said here is I could have said this, negative x minus 2. Because isn't that mathematically the same thing? ln of negative x minus 2. If I distribute in the negative, then that would have said to me, okay, that's a reflection, then a right 2. That would have gotten us to the same location. Okay? Still ending up with the same asymptote. Did I do everything it asked me to do? Describe the graph, the transformation, find the asymptote. Yep, good. So again, moral of the story here is that anything exponential, a vertical shift, anything happening vertical to it is going to change my asymptote. Has the possibility of changing my asymptote. Anything for a logarithmic, anything happening horizontal, any shift horizontal is going to change my asymptote. Remember that the exponential asymptote is always a y equals, the logarithmic asymptote is always going to be your x equals. Okay. All right, let's chain them together. Let's now write them. This was just seeing what they were based on the equation. Now let's write them. F of x is equal to 4 to the x. That's my parent. It's reflected across both axes and then moved down 2. So let's see what happens. Here's my g of x. All right, so let's perform the reflected across both axes. Well, that's nice. I don't even need to remember where it goes. I make them both negative, right? Down below and up in the exponent. Be careful. What is the base of my exponent still? Just 4, not negative 4. Remember, we're never changing the base. And then moved 2 units down. Oh, sweet. Minus 2. Done. You're going to find that writing these functions are a lot easier than the ones that we've done in the past because there is no simplification at the end. You can't really do anything with these exponents because you're so restricted to where it goes. Like for this, f of x is equal to ln of x. That's our parent, the natural log of x. It's compressed horizontally by a factor of 1/2, then moved 3 units to the left. All right, so this is a tricky one, compress horizontally. Remember, horizontal compression. Horizontal compression takes f of x and maps it to f of 1 over bx, right? So that means that if I've got a horizontal compression by a factor of 1/2, that's going to turn into, f of x is going to turn into f of what? Flip it, 2x. Okay, that's a horizontal compression by 1/2. You got to take the reciprocal of that value. That's the only tricky part today. All right, so let's do the horizontal compression part first. So we say, okay, g of x is going to be, halfway there is going to be ln of 2x. Any simplification to do? No. And then it says, okay, I want to move it 3 units left. All right, well, 3 units left is going to take f of x and going to map it to f of x minus h, so x plus 3 inside parentheses. Now be careful here. Be careful. What does something horizontal do? It removes x, so g of x, my final, is going to be ln of, it was 2x, now it's 2x plus 3. It's going to remove x and input whatever's inside the parentheses. Why does that change anything? Because you might try to say 2x plus 3, but it's not. It's 2x plus 6. That's my answer. All right, so transformations, not that bad, right? Not that bad. I am totally fine with you graphing them in your calculator and using your calculator to sketch the graph. Just so you guys know where we're headed, again, today we're doing we did section 7.7. Tomorrow we'll do section 7.8. Wednesday, we're going to review, and I'm going to give you a review on Canvas, and then I'm going to post the key like right away. It'll be posted with the review. It's not like a regular homework assignment. It's just going to be a review assignment, suggested problems that you should do. Thursday, at the beginning of class, I'm going to spend about 15 minutes for you guys to ask me any questions. And then the rest of the day on Thursday, we're going to take part 1 of our test. We're going to take the no calculator portion, and that is a no calculator. We'll take the no calculator portion of our test on Thursday, and then we'll take the calculator portion of our test on Friday. Does that make sense? Okay. Again, this isn't really like a full 2-day test. It's kind of like a 1.5-day test. That's why I'm going to allow for any questions to be asked on Thursday if we need to. All right. So long, everybody watching at home.